Okay. What I want to do here is I want to talk about polyprotic entities, and then I'll talk about pH. We have polyprotic entities, pH, curve, and shape, and type, and then some actual titration questions like titration stoichiometry. What I'm going to do here is talk about polyprotic entities and kind of end the lecture here, just because it's a lot of information. So polyprotic, right, we talked about, so amphiprotic or amphoteric could be polyprotic entities. So species that are able to either donate or accept more than one proton, they exist on your acid-base chart. So you have H2CO3, oxalic acid, HPO4 2 negative, CO3 2 negative. So they can be both bases and acids, right? So the first proton accepted or donated will always be easier. So just a couple facts about this. When we talk about reactions, I'm going to graph this on a titration curve. So the first proton accepted or donated will always be easier to accept or donate than the second or third one. And this is because of Ka and Kb relationships. So polyprotic entities permit multiple equivalence points to happen. Here's the deal though. Only quantitative reactions produce detectable equivalence points in acid-base titrations. So when there are no potential products left that can react with water, we are done. Okay? So we'll have equivalence points when the titrations go to completion. All right? We've talked about the 5-step method to identify entities, so I'm going to do that here. And the first step is always quantitative, but the endpoint reactions together, you put the endpoint reactions together to get the net ionic reaction, and then we can find acceptable indicators at each step by looking at the graph. So I'm going to give you a bunch of examples here, but page 759, numbers 5 through 10 deal with polyprotic titration curve. So let's look at this one. So let's say we have 25 milliliters of 0.50 mole per liter Na2CO3. So sodium carbonate titrated with 0.50 mole per liter HCl. All right, so the CO3 2 negative is a base. All right, so remember, this is going to end up being 2Na plus and CO3 2 negative. Okay. I'm not going to write all these increments. But what we have is we have an equivalence at 8 and we have an equivalence at 4. All right, so with a polyprotic entity, I'm going to have multiple endpoints. Okay, so the CO3 2 negative can take on a hydrogen to become HCO3 negative, and then can also become H2CO3 if we keep adding acid. All right, so I would use something like phenolphthalein here, and then if I look on my indicator chart, I would use something like methyl orange to figure out when I'm at each endpoint. Okay? So, this is what a multiple polyprotic titration curve can look like. I'm going to give you a word problem here, and we're going to construct this. Okay, so here's where this graph came from. So the word problem says sodium carbonate is titrated with hydrochloric acid. And let's say this is an excess, so it's not a limiting factor. Okay? What is the titration curve of this reaction? Okay, so the titration curve is going to be this. So I've shown it to you. Okay? Now let's go through the process. So I have sodium carbonate. So this is Na2CO3 plus HCl. So first thing I need to do is identify my entity. So I have Na plus, CO3 2 negative. We're going to have hydronium from this, Cl negative, and H2O. Okay, now I have my strong acid and strong base here. So this is what the first reaction is going to look like. So it's CO3 2 negative plus H3O plus, and the first reaction is quantitative. So what happens is we make HCO3 negative, right? This donates a proton plus H2O. All right, so this is reaction 1, and then in between here is reaction 2. Okay, so we can continue. So acid continues to be added. To the sample from the burette. All right, so with these polyprotic entities, we're going to keep reacting until all of the sample is used up. So what we have is